I welcome you all to this round of lecture annotation video. So today's topic is about error detection. In the previous lectures, we had discussed about how we are transmitting the signals, how data are processed in the sender side and the receiver side. How can we send multiple signals or data from multiple channels in a single link, etc. So now we are focusing on the effectiveness of data communication, which is known as accuracy. So accurate data is the data that we get from when what message when the message that is transmitted from the sender side and received in the receiver side are the same. That message we term it as accurate. So now let's begin. So this is week 10 topic, error detection and correction. So let's move on forward. So this is the background that I'm going to just read it about, that network must be able to transfer data from one device to another with acceptable accuracy. Now this term will vary. What do we define by acceptable accuracy? The term acceptable accuracy, in some cases, that some pixels or some values might be changed and it is tolerable, and otherwise no change to the messages or data are acceptable. So and this term is known as acceptable accuracy. For most applications, a system just guarantees that the data received are identical to the data transmitted. Anytime data are transmitted from one node to the next, they can become corrupted in passage. That is, they can become corrupted or error prone during the transmission from one place to another. So many functions can alter one or more bits of a message. Therefore, some applications require a mechanism for detecting and correcting these errors. So we are going to focus on how we can detect and correct these errors. So let's move on forward. The first thing that we have to know that how many types of errors are there. The two common types are single bit error and burst error or multiple bit error. This is multiple bit of error. So just let me write it down. Multiple bits of error occurs in a single data transmission is called burst error. So whenever bits flow from one point to another, they are subject to unpredictable changes because of interference or transmission impairment. We know it very clearly. There are three types of transmission impairment. If you do not remember them, take a look at the mid contents. So I think you would get the idea. This interference can change the shape of the signal. So the types and why these changes or errors, what effects does it make is already mentioned in here. So let's move on forward. I hope you get that. So this is the single bit error, the demonstration that I have already told you about. This is the sender side. I've already told you about that. Always the left hand side is for the sender side and the right hand side is always for the receiver side. So this is the formal definition. You will read it and memorize it. So what happens here is that a single bit error is changed. This is the total sent data. and this is the total received data. Only a single bit 0 is transformed into 1. So this single bit error is a type of this error. So let's move on forward. We are going to see about burst error. So what happens here is that in a period, say this is the whole of the sending message, and we have received error in this position in the receiver side, and this position. So what happens here is that the first bit that where the error occurs, and the last bit the where the error ends, that is this starting error and this starting error and this ending error, including these bits, this number of bits, say for example 1, 2, 3, 4, 5, 6, 7, and 8. This 8 bits includes 4 errors. So this 8 bits is the length of the burst. That is, in this portion, in these 8 bits, there are multiple errors. So when we transfer data, binary data from one place to another, the only error that can happen is to change a bit from 1 to 0 and 0 to 1. So this is known as the burst error. So I hope you get that. So let's move on forward. Now the concept of redundancy comes to our mind. What is redundancy? The central concept in detecting or correcting errors is redundancy. The central concept that is a core solution to resolve the error is redundancy. What does this redundancy do? It enables the sender and the receiver both to add some bits extra to check the reliability of the messages or data that are being transmitted from one point to another. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct corrupted bits. So redundant bits are kind of extra bits that we add with the message that we have seen during the header and trailer information addition in the previous lectures. So that is what we call them, the redundancy, to enable the receiver to get the full view, to double check the message and see if there is any error in there. So that's it. I hope you get that. So let's move on forward. So now, how the error detection works. So in order to correct the errors, we at first need to detect them, right? So that's what is we require to know. So this is the process how we can detect the errors. The transmission is always unreliable. So if we say that there is a reliable transmission, we are just kind of theoretizing in the ideal scenarios that the transmission there is no impairments, no interference, etc. So how can errors be detected? By using block coding. So these block coding techniques are not directly our line coding schemes, etc. So block coding, if the two conditions are met, the receiver can detect a change in the original code word. So in block coding, we had previously kind of talked about these extra bits, m bits to n bits, uh, m bits frames. We convert them to n bit frames and added some redundancy, some header and trailer values, etc. So this concept is being used in here. If two conditions are met, the receiver can detect a change in the original code word. The receiver has or can find a list of valid code words. This is the capability of the receiver. And number two, the original code word has changed to an invalid one. So if there is change in a specific pattern and the receiver can get the list of the valid code words, we can detect the errors easily. So this is what being happened in here. So this is the traditional, the sender side, and this is the receiver side. And in the sender side, we always encode the message and use the encoder. So the actual data word or the message is of k bits, and we generate some extra bits and add and generate this code word which is of n bits, and we have to remember that k is always less than n. So we have to remember this always. So when we send this code word to the receiver, the code word is received by the receiver. Then we check the code word, and if there is no error, if we cannot detect any error, we proceed and extract the data word, which is definitely of k bits. Otherwise, we discard the code word and request the sender to transmit again. So this is the whole process of error detection. This is how it works. So the first technique of this error detection is Hamming distance. So one of the central concepts in coding for error control is the idea of Hamming distance. So Hamming distance is the number of differences between the corresponding bits. So we show the Hamming distance between two words x and y as d, d for the distance x, y. So this is the example right here. If the code word is 5 zeros is sent and 3, and a code word of 01101 is received, 3 bits are in error, and the Hamming distance between them two is this value 3. In other words, if the Hamming distance between the send and the received code word is not 0, the code word has been corrupted during transmission. So this is all that is about. The Hamming distance can easily be found if we apply XOR operation. We are very familiar with this topic. You have gone through this topic in your digital electronics class. So XOR operation is very familiar to you guys. So if we perform this XOR operation on two words and count the number of ones in the result, we can easily find this Hamming distance. So let's move on to another example to get a clear concept. So we are given two data word or code words or whatever. Specifically, we are given two pair of words. So we can consider them as code word because the data word is the extracted message. So we get the code word first. So this is a word or code word, and this is another word, and this Hamming distance is 2. Why? So let's take a look. I will point this as virtually to get a more clear concept. So when we perform this XOR operation, we get 1 1 and a 0. So if we count the number of 1, that is 2. So the Hamming distance of this two word, this is the first word and this is the second word, is 2. And for similar reason, the Hamming distance of these two word is 3, because when we perform XOR in this scenario for these two words, we get 3 ones, and this is the Hamming distance. So what do we mean by minimum Hamming distance? So minimum Hamming distance is the distance, smallest Hamming distance between all possible pairs in a set of words. So what we will be given in our exam is kind of more than two words in a group, and we have to check each other uh, for the Hamming distance, and the least value of the Hamming distance is the minimum Hamming distance. Say for example, I will give you A, B, C, three words. So one word is 101, another is, say for example, 110, and another is 100. So now we have to, in order to find the minimum Hamming distance, we have to consider the Hamming distance between A and B, and the Hamming distance between A and C, and also the Hamming distance between B and C. The lowest value between these three particular Hamming distance is the lowest or minimum Hamming distance, or the minimum Hamming distance. The highest value between these three Hamming distance is the maximum Hamming distance. So to guarantee the detection up to S errors in all cases, the minimum Hamming distance in a block code must be D minimum S plus 1. So what does this particular block of theory means is that if we want to detect 2-bit error, the minimum Hamming distance of that particular block code needs to be 2 plus 1, that is 3 bits. That is D minimum should be 3. If S is equal to 2, then D minimum should be 3. So this is the minimum Hamming distance. So I hope you get that. And these examples will be your self-study. I have already given you this concept. So I hope you get this. So let's move on forward. So these are the similar kind of examples. So you will have to, it would be your self-study. So what is the error detection and correction capability of this scheme? So here we get another important topic right here, that in other words, if this code is used for error correction, part of its capability is wasted. Error correction codes need to have an odd minimum distance, 3, 5, 7, etc. So this example is kind of extra information, contains extra information. I think you would get that. It's not that difficult for you. So next topic is parity checking. So you are familiar with even parity and odd parity and everything about parities. You are very familiar with it. You should have implemented a parity checker in your digital electronics course. So I'm not going to the details. So how you can calculate this odd parity or even parity or and everything. So this is simple and two-dimensional. I'm just going to read it about and then try to explain if there is some concept alien to you. In parity check, a parity bit is added to every data unit so that the total number of 1 is even in case of even parity or odd for odd parity. So that is what happens. So this is a deviation from our normal procedure because sender side is portrayed in right side here. So what happens is here is that we get a data, and to calculate the parity that we see that we should add another one to enable this data contain even number of ones. So we are going to generate a even parity right here and then send this total data via the transmission medium to the receiver node where the bits are counted, and if the number of bits 1 bits are even, then we accept the data and we drop the parity bit and accept the data finally. But if the number of ones, that is the parity, is uneven, that is odd, then we reject this data. This is the format how this parity checking works. So let's move on forward. So this is the encoder and decoder of simple parity check. So the checker in the generator is always in the sender, and the checker is always in the receiver. So what we do here is that we add this data word and generate the parity bit, and we send this code word to the receiver, and the receiver gets this code word, receives this code word, and we check this code word with a syndrome which gives the values of the parities that should have been in the code, and then we decide, like the flowchart, whether to accept it or discard the data word. So that is what being done in here. So I hope you get this process. If you have any problem, feel free to consult me when we resume in Google Meet. So this is the example. So therefore these are the words that we require to send. These 5 are the bit strings that we send from the sender. So what we need to do is add a parity bit so that these data are transmitted with some correcting ability. So I think this should be your self-study. But if you have any problem, feel free to ask me in the Google Meet session. So let's move on forward. Now this is the continuation of the example, so I'm not going to delve much deeper. I think you should get it, but I think you might have possibility of misunderstanding this continued example. So I will tell this in details in your Google Meet if you require it. Now, another process that we use is cyclic redundancy check, or in short, we call it CRC. So what does it do? It it does a binary division on the data and add that value, the remainder, with the CRC and process the data to generate the code word, and which in turn is verified by the receiver side by using that particular divisor. So let's go into the details. At first, I'm going to read out the slide and then go into the details. So at the first point that we see here is that it uses binary division. So it uses the binary division, and then add the CRC remainder to the data to generate the CRC code, or cyclic redundancy check code. The number of zeros append is less than the divisor. So when we divide, the number of zeros that we are appended is one less, that should be one less than the divisor. The appending CRC to the end of the data must make resulting bit sequence divisible by the divisor. So that is what happens, that we add the bits with the remainder, that this n bits, and this n bit is added as CRC, or the redundancy check code, and transform this total as code word. And what we had to remember is this, that the divisor size is always one bit greater than this redundant bit. Number of redundant bits is one bit less than the divisor bits. So when we get to an example, you would this would be quite clear to you. So before that, in the receiver side, what it happens is that they receive this total code word with the CRC code, and then use that divisor. These are two are same kind of divisor, and when we get a 0, we accept the code, or accept the message, and when we get a non-zero, we reject the message or the data. That is what happens. So let's move on forward. So this is the process. We need to generate the CRC code. So what happens here is that this data word is of 4 bits, and these 3 bits are redundant bits, R0, R1, R2. These are the redundant bits, and the divisor that is known to both to the sender and the receiver are kind of similar, are actually same. So what we we are seeing here is that there is 3 bit of the redundant bits and there is 4 bits of the divisor, and then we generate this code word and send it to the receiver via the transmission medium, and then it is subjected to the checking or checker, which results in this 3-bit syndrome, which is corresponded which is kind of similar to the redundant bits. And using these redundant bits or syndrome, the decision logic decides whether to accept the data word or to discard it. This is the overall process. So let's see further example. Multiply is and subtract is XOR. So kind of we will get to it. So this is the divisor, this is our data, this is our number of redundant bits. So when we try to divide these total values with a divisor, what happens first is that it only goes once. So when we multiply 1 with the divisor, it gives the similar value with this divisor. 1011 was the divisor, and when we multiply it by 1, we get the value 1011. Then what happens? We are subtracting this value from this one. So what we are executing is XOR. So this kind of gives us 0, and it is not required here. So we are considering these 3 bits, potential bits. So 0 and 0, when we execute an XOR operation, we get a 0, and then when we get 0 and 1 and we use this XOR operation, we get a 1, and when we get 2 ones and execute the XOR operation, we get a 0. This is what happens. And then we take another bit from the remaining portion, and then we divide it by multiplying the divisor by 0. That is, there is no way a number of 4 bits can be used to divide a number of 3 bits. The the most significant bit 0 is not calculated here, or not of significance actually. And now again we discard this bit and execute the XOR operation again. So what happens here is that only this bit 1 and 0, when we execute the XOR operation, we get a 1, and then for this double zeros we get a 0, another 0, and then this bit just comes into play, and here we get a bit of 4-bit number, and now the divisor can perform its dividing operation, dividing operation. So we multiply it by 1, and then we perform the XOR operations. So what do we get right here is 0 1 1, and then for the last remaining bit we get a divisor multiplication with 0, and we get all bitwise zeros. When we multiply, we use this operation, that is 1 0 1 1. We multiply it by 0, then it is we execute the AND operation. For every bit we multiply it by 0, and when we know that if both inputs are not 1, then the output for AND is always 0. So this is how we get these 4 zeros, and this remainder, that is what we are adding right here, is the code word. So I hope you get that, but if you do not, please I will ask me and I will explain you it further in your Google Meet session. Now, what happens in case of the receiver side in the decoder? So what do we have here is the uncorrupted version of the message that we are sending from the receiver side. So here is a mistake. This should be a decoder. In the receiver side, we get this total code word, right? And this divisor is familiar both to the sender side and the receiver side, both to the decoder and the encoder portion. So now what happens is that we will divide this entire code word with the same divisor that was available for the decoder, and at the end we will get a 0, which is the redundant bit in the receiver side, and we name it syndrome. So when we get this syndrome as the values of 0, then we accept this data word, and if a bit had been corrupted, we would get non-zero as the syndrome value or the redundant bit value, and then the data word will be discarded. So this is all about how we detect any kind of errors. Now, in order to correct them, we need to ensure that where at which position this error had happened, and we would eventually be able to flip that bit to the correct one. So that is for your topic for another day. Hopefully when you get more concept about this course, data communication. So this is all about today. This is all about the error correction for today. Thank you for watching and listening to my lecture annotation video. I hope you understand it, and I will definitely ask you about the problems or the corrections that I have given in this slide and the self studies. See you in next lecture annotation video. Thank you all.